So this is our second application of Biot-Savart's law, and it is again finding the magnetic field at a point on the axis of a current carrying coil. So we have a current carrying coil over here. Now this coil is kept in YZ plane, okay? So and its axis is lies towards x-axis, right? So this is perpendicular to this plane. So this is the coil and this is the axis like that. And now this current carrying coil is having a current I in this direction. So which is like, if you look from this direction, then it is, see, it is anti-clockwise, right? Now from this direction it is anti-clockwise. And now there is a point P on the axis at a distance x from here, and the coil is having capital R radius and small r is the distance from the edge of this. Now if you get the distance from here also, that is also going to be r, because this is r and this is capital R. This is capital R, this is x, and this angle will still be 90. So this is again small r only. So small r is the distance from all the entire edge, right? This is the, from this or from this you take any point that is at small r distance. Now let us say that due to symmetry, now what I am going to do is all these small element on the ring, right, or the coil is going to produce magnetic field over here. So I will take the dl on entire small sections on the ring. So I am saying take two, one at over here and one at the other end, the diagonally opposite end, right? So these two dl vector, now due to this dl vector, again this is important that due to this dl vector, what will be the direction of magnetic field over here? It is out of the plane. At this point current is coming out, right? It is half, it is like this way. So it is coming out of the screen, and the r is that way. Do dl cross r, right? So direction of magnetic field, dl is outside, right? And r is this way, right? So dl cross r, in the direction of r your palm should be facing, okay? In the direction of l, dl, your fingers must be facing. So dl cross r, now your thumb is pointing that way, right? So that way is basically from here that way. At this point, this is my dB vector produced by this dl, small elemental dl. This is my dB vector. So let us say this angle is theta. So I can divide my dB in two components. One is dB cos theta and another is dB sin theta, right? Take that into mind. Now look at the other small element at the bottom of the screen. Now this is coming out while the other way is, it is going into the plane of the paper. So again I am saying dl cross r. From here the r is that way. So dl cross r. If you see my thumb, it is that way, right? So from this r, it will be basically this side. And due to symmetry again, it was this and that 90 degree. It is same. This is r, this is x only. This is r only and this is capital R only. So these are identical, and eventually this angle is again going to be theta. And this is again going to be dB only. So again make two component, dB cos theta, dB sin theta. So this dB sin theta will be cancelled by this dB sin theta. What about that way? That way dB cos theta, all such dB cos theta are going to be adding up, and eventually it will give me the overall magnetic field. Okay, overall magnetic field at that point P. Now I will simply say that here what I am going to do, I am going to find the small magnetic field dl due to this at point P. This is my dB. I will just take dB cos theta component. I will integrate my dB cos theta, and that way I will get my entire magnetic field. So let's do the derivation. So I will simply say that my total magnetic field is nothing but integration of all dB cos thetas, right? dB is what? Magnetic field produced by this element. There will be a lot of element which are producing, and all are forming the same angle, right? Because due to symmetry in 3D, if you see it is symmetry about the x-axis, right? So dB cos thetas, I am just going to integrate all of them. Now it is time to write dB. How do you write dB? dB is what? Mu naught upon 4 pi, using Biot-Savart's law here. I, current is still I, so I dl cross r or dl sin theta. I am not using r because if you are writing dl cross r, then you have to write r cube over here. So I am saying dl sin theta. So what is my dl vector? dl vector is dl here. What about sin theta? Which sin theta? The angle between dl and r. Now your dl is out of the plane here and r is like this. So angle between them is going to be 90 degree, right? here at this point, DL is going to be downward, R is that way. So angle is always 90 between DL and R. So I am not going to write, or we can write sine 90, or we can just avoid that. So I am writing sine 90. This theta and this theta is different. Okay, this is the angle between DL and R, while this is this angle cos theta which we have assumed here, upon R square. So what is the distance? Distance is R only, so upon R square. And then there is another cos theta. This is entire thing is my dB using Biot-Savart, and now I am saying it is cos theta, and now we have to integrate. What are the variables here and what are the constant? If you see, mu naught upon 4 pi, that's a constant. Then I is also constant. DL is like variable, right? It's DL, so small length. What about sine 90? It's 1, I am not writing. What about cos theta? If you take this DL or this DL or this DL, for any DL, cos theta is like always, if this is theta, this is 90, right? This is 90 minus theta and this angle is theta. So if wherever you check, the theta, cos theta is always capital R upon hypotenuse small r. So cos theta is another constant. For all it is capital R upon small r. And now there is R square over here, so I am writing R cube. What is left is DL. And I simply have to integrate that. And what is the integration of DL? All such DL add up and give me this entire length of the coil, which is nothing but 2 pi R. So this thing is 2 pi capital R. Now, if I replace that with 2 pi capital R, then I get my formula, and I will say, instead of this, keep 2 pi R and simplify for the final formula. So this is 2 pi R, and now this pi and 2 gets cancelled and I get 2 over here. So I get mu naught I R square, right? Mu naught I R square over 2 R cube. So 2 and R cube. What is my R? R is, X is the distance of point P, right? From the center or on the axis. So X square plus R square root is, so this R is nothing but square root of R square plus X square. So there is power half and then cube. So power will become 3 by 2. And that's the field on the axis of a current carrying coil. What if there are n turns? Instead of 1 turn, see, if there are n turns, then we can simply make it n times. So single coil is producing this much. If there are n number of turns, then it will produce n times the magnetic field of this much. So we can say it is mu naught I R square upon 2 R square plus X square raised to power 3 by 2. Now there are some special cases. So first is like, let us just discuss the magnetic field is directed along the axis. If you again see the figure, so this is the figure and this is the axis is x-axis. At this point, the direction of net magnetic field was coming like this, which was nothing but integration of dB cos theta. So direction is along the axis only, and that you can get using right hand rule. So just turn your fingers in the direction of the current in the coil. So like this, and the thumb will tell the direction. So direction over here is like that, and at the same time, if you are checking here also, the direction of magnetic field is always like this. So using right hand, this is my right hand. So using right hand, you can get the direction of magnetic field on the axis. So direction of magnetic field is always along the axis. Now, next is the field strength is maximum where x is 0, and when x is 0, what does that become? If x was the distance on the axis, if x is 0, then we get the center of the ring, right? And how much it is? So just put x is equal to 0 in the formula. Our formula was mu naught I R square divided by 2 R square plus X square. X was the distance on the axis raised to power 3 by 2. Just put x is equal to 0, and this becomes power half cancels. This becomes R cube. So we get 1 by R. So it is mu naught I by 2R. So this is the formula on the for the magnetic field at the center of a ring, right? Or center of a coil. If there are n turns, you can simply make it n times. This is just due to a single turn. And now last is at very large distance. If we are saying x is too much, x is way greater than R, then what will you do? Again, you can say that it is mu naught I R square upon 2 R square plus X square raised to power 3 by 2. Just neglect R now in the addition. So you'll say it will become x cube. So it is 2x cube in the denominator and IR square in the numerator, right? So this is the formula. This is the formula for very large distance. The significance of this we will discuss then when we learn the magnetic dipole, right? So this is like due to dipole also, like a current carrying coil behaves as a magnetic dipole. So this is especially important. So as of now, you just remember it. So you can remember the original formula and put R is equal to 0 in that. Just in the, like, you can neglect it here. We cannot neglect it here because it's in multiplication. So just neglect R in addition and eventually we will get this formula. Let's do a question. So this question says that a 6.28 meter, that is 2 pi, okay, long wire is turned into a coil of diameter 0.2 meter, right? And a current of 1 ampere is passing in it. Now the magnetic induction or magnetic field at its center will be, just write the formula for magnetic field at the center. It is mu naught I by 2R. We have to get some certain things. First is radius. Radius is half of the diameter. So that's 2 into 0.1, right? Next is mu naught. Mu naught is basically how much? 4 pi into 10 raised to power minus 7. And current. Current is also given, right? Current is how much? Current is 1 ampere. But there is a issue. Issue is what? If you check, this is the long wire, and now if you are making a coil, there will be more than one turn. This is magnetic field due to just a single turn. So you have to do into number of turns. How can you find the number of turns? You will say that 2 pi R, R is 0.1 into number of turns. That should be the length of entire wire, which is 6.28. If you see, this is 2 pi, this is also 2 pi, it gets cancelled. This is 1 by 10, so N comes to be 10 turns. So there are basically 10 turns in the coil. Okay, so there are 10 turns and we are getting the magnetic field at the center. So we have to multiply the magnetic field due to single into 10, right? And eventually what does that give? This gives me 2 pi. So it is 2 pi, which is 6.28 into 10 raised to power. This is minus 7, minus 6 and further 1. So minus 5. So 10 raised to power minus 5 and unit is SI unit, which is Tesla. So this is the magnetic field. Answer would be A. Now, this is our next question. It says a uniformly charged ring of radius R carrying Q charge, okay, carrying Q charge is rotating with an angular speed omega. Find the magnetic field at the center of the ring. See, you need to understand that this is my ring and this is carrying total charge Q. I am just saying that, let's say entire charge is over here. Now, if it is rotating with a angular velocity omega, then see, rotating, the ring is rotating. So eventually this charge is moving like this with the ring, right? So I will say that the current, first idea is to get the current. Current is how much? Current is charge upon time taken. So total charge is basically Q and time it takes to one complete rotation is the time period, and that is 2 pi by omega. And eventually that gives me my current to be Q omega by 2 pi. So that's my current, right? So current is Q omega by 2 pi. And now next is to get the magnetic field at the center of the ring. So I'll just apply the formula for the center. It is mu naught I by 2R. And what is the radius? Radius is already given. It's capital R. It's just mu naught is constant, 2R is given, and I we have found in the given parameter. So answer is going to be mu naught Q omega by 2R into 2 pi. So that becomes 4 pi R. And that's the answer. We'll leave our answer like this because all the parameter given to us are variables. So we'll keep our answer like this. Now, this is another question. It says that two similar coils are kept mutually perpendicular such that their centers coincide and they are similar coils. Similar coils means their radius are equal, right? So, and their mutually perpendicular means one is in XY plane like this and another is in YZ or XZ plane, right? So these are basically rings which are kept like this, and now they are saying that at the center find the magnitude of the at the center find the ratio of the magnetic field due to one coil, magnetic field due to one coil only, and then and the resultant magnetic field through both coils if the same current flows. So if same current is flowing, then magnetic field at the center due to each is going to be same. It is mu naught I by 2R, and R is same because they are similar coils. Current is same, it is given. So magnetic field, let's say, due to individual is B. So now you just look, and direction is along the axis. So due to this, let us say due to this, the direction of magnetic field is this, and the magnetic field produces B. What about due to this one? This one is lying in this plane, okay, the horizontal plane, and this was in vertical plane. Okay, so due to horizontal plane, let's say the magnetic field produces B and it is in this direction. Now what is the net? Since they are vector quantities, the net is going to be their vector addition, which is this square plus this square root, so root 2B. And they are asking which ratio? The ratio of magnetic field due to 1, which is B. So answer is magnetic field due to 1, which is B, divided by resultant magnetic field. So answer is 2B, like root 2B. So this upon root 2 resultant, which is root 2B, and you can cancel out B. Answer is 1 by root 2. For this question, you don't even need to remember the formula also. It is like without putting the value of B, we can directly get the answer. So answer is 1 is to root 2. This is our third application of the Biot-Savart's law, and here we are going to find the magnetic field at the center of an arc. It is just an arc of and it is carrying basically some current. Okay, now this is the arc having I current, and we are just going to find magnetic field at this point, which is basically at this point where it is subtending an angle of theta, and radius of the arc is basically R, as you can see. So I have to get the magnetic field due to this arc. What I am going to do is, I am saying that this is basically just take dl over here. At anywhere I am taking this dl. So this is my dl, and due to that this is my r vector, right? Angle between dl and r vector is basically 90, as you can see, because the dl is always going to be tangential like that. So this angle is all. I am just writing the magnetic field due to that small element dB, and that's using Biot-Savart's law. It is mu naught upon 4 pi I dl sin theta, right? I dl, and sin theta is sin 90. So I dl upon the distance is square. So the distance is same as the radius, so square. So that's my dl. And if you check the direction, then dl cross r is into the plane. So at O, it is into the plane of the paper. And due to all dl, it is into the plane of the paper only. dl cross r, right? So I can simply add such dB. So I'll say integration will give me total magnetic field. Now if you see, in this everything is constant. For any dl, the distance is r only, right? The angle is always between dl and the r. Okay, dl and r vector is always 90 degrees. So I don't have to write anything over here. So I'll say it is mu naught upon 4 pi r square, and there is I, and integration of dl. What is integration of dl? It is simply this length, right? So integration of dl is nothing but r into theta, right? So integration dl is r theta, which is this length. And you can cancel 1 r over here. So we will simply write it as mu naught upon 4 pi r and I. So this can also be written some other way around. What is that? And there is theta also. So this is the way you can remember it. Now there is another way to remember it, is like if you check due to the entire coil, it was what? Mu naught I by 2R, right? At the center. So due to entire coil, it was mu naught I by 2R. And now you say we just have theta part of that out of total. So I'll say into theta upon total, which is 2 pi. You will get this formula. So this is a simple way to derive it, or just a way to remember it. You say the total is this due to the entire coil, and you take theta part out of 2 pi. So eventually we get this formula, which is mu naught I theta by 4 pi r. This is the magnetic field due to an arc. I'll be remembering it in this manner. Mu naught I by 2r into theta by 2 pi, right? Now, let's see some questions of this type. So a wire loop formed by joining two semicircular arcs, okay, of radii R1 and R2, which are carrying current as shown in the figure. Both are carrying I current only. Like this is a carrying I current, same I current is coming, and this is semicircular, this is semicircular, right? So they are saying the magnetic induction at the center O is. So if you see that due to this part, so what is the magnetic induction? Just curl your finger. That for direction you can do either dl cross r, so into the plane of the paper, or you can simply curl your right hand finger in the direction of current. So direction of current is into the plane of the paper due to this. Due to this, again do the same thing, curl. So it is due to this one or this one, the direction of current is into the plane of the paper. So I can simply add both of them. That will be the vector addition. So I am saying it is due to this plus this. What about these two parts? If you see these two parts, this is a finite wire and point O is lying on the line of the wire. So this is not contributing in the magnetic field at all. Similarly, this also, this wire, the point O is lying on the line of the wire. So this will also not contribute at all in the magnetic field. So magnetic field at point O is only due to this part, and we can simply add them because both are having the same direction. So I'll be saying that total magnetic field is magnetic field due to this semicircle, which is how much? See, mu naught I by 2r is due to full, and half of that, because semicircle, so theta upon 2 pi is like pi upon 2 pi, so half of that. So mu naught I by 4r. So mu naught current is nothing but I by 4. And what about r? This is having a radius r2 plus magnetic field due to this is again mu naught I by, this is also a semicircle, so mu naught I by 4r and radius is r1. So you can simply take mu naught I by 4 common, and it is nothing but 1 by r2 plus 1 by r1, or 1 by r1 plus 1 by r2. If you want, you can leave your answer like that, or whatever is the option, just form your answer as per that. Now moving to next question. So the question is, consider the circular loop having current I and with central point O, the magnetic field at the central point O is. So there are like this is one part of the circle, and this is like a straight part. This is another part of the circle, and this is again a straight part. So current flowing is I in the entire thing. Now first thing is, due to this part, the O is lying at the line of the wire, so this is not going to contribute at all in the magnetic field. Similarly, this part is also not going to contribute at all in the magnetic field at O, right? Now it is only due to this and this. Now first have a look at a direction. So we are saying that it is clockwise. Clockwise is into the plane. Due to this, again it is clockwise, so into the plane. So overall it is into the plane, and both are into the plane. So I can simply add both of them in magnitude. So I'll be saying acting upward is the wrong option. Now let us get the magnitude. So direction is downward, downward, or downward only, that is into the plane. So all these three options are correct direction wise. Let us get the magnitude. So due to this part, it is basically mu naught I by 2r, and radius is how much? It is r. And then how much part of full? It is 3/4 as you can see, or you can also go like this. It is 3 pi by 2 divided by 2 pi, right? Theta upon 2 pi plus, due to this one, it is again mu naught I by 2r. What is the radius? This is 2r and this is r. So total radius is 3r. And then how much part? 1/4 part of that. So this is full and this is 1/4 part, or you can also go like theta upon 2 pi, where theta is pi by 2. So pi by 2 upon 2 pi. Let's just simplify this. So mu naught I we can see everywhere, divide by r is also there in all of them, and this is how much? 3 by 8 plus this is how much? 1 by 24. And when you solve this, we get how much? So 24 is LCM and we get 9, 10. So 10 by 24. So 5 by 12. So 5 by 12 mu naught I by r. That's the magnitude, and direction is into the plane. So which option is correct? 5 mu naught I by 12 are acting downwards. Downward simply is not this direction. Downward is into the plane of the paper.